So remember the concept of probability mass function for discrete random variables. This was a graph that showed us the distribution of the probability weights across the different values that the random variable can take. Here's an example. Perhaps this is the probability mass function for a random variable that tracks the number of customers who enter a store on a randomly selected day. Maybe it takes values either 1, 2, 3, or 4. Hopefully that's not actually the whole day, maybe per hour here. But the point is, this keeps track of which values are more likely and which are less likely. And also recall that we can do calculations. For example, the probability that x, the number of customers, is equal to 2 can be found here on the probability mass function and is equal to 0.2. Similarly, the probability that x is greater than 1 but no greater than 3, in other words, the probability that x is equal to 2 or 3, is also found on the probability mass function here by just adding the two weights. 0.2 plus 0.25 equals 0.45. So there's an analogous concept for continuous random variables, but it has to change a little bit because remember, we can't list out all of the values along the x-axis. So let's say you're interested in the amount of rainfall in centimeters, and this is your continuous random variable. You'll have something that looks like this. It's called a probability density function. It's sort of a smooth version of what you see on the left for the discrete random variables. And this will also allow us to do calculations. Let's ask first the probability that x is equal to 5. And by this I mean 5.000 to an infinite number of decimal places. So this is a little bit different, a little bit tricky. The probability of this happening is actually 0. It'll virtually never be exactly 5 centimeters. And that's true of any single value that you'd like to calculate a probability for. However, you can still use this to calculate probabilities in ranges. Realistically, you may be interested in something more like this, the probability that the rainfall is between 5 and 10 centimeters. And this works, and it's just equal to the area under the curve between 5 centimeters and 10 centimeters. Now, if you wanted to get an exact number out of this, you'd have to use calculus, and you won't be required to do that in DMD, except for very, very simple distributions where calculus isn't necessary. However, the intuition is important to see that just like on the left-hand side, the heights of the bars reflect different probabilities. On the right-hand side, the height of the function tells you which ranges are more likely and which are less likely. For example, way up in the higher range, you see that the probability becomes much smaller. So higher values of higher amounts of rain per day are less likely for this random variable. Now, recall one more thing about the probability mass function. It must be the case that all of the probabilities add up to 1. And in the continuous case, there's an analogous property. If you were to take the entire area under the whole curve, this would also have to be equal to 1. And this makes it so that the probabilities work out correctly according to the probability laws that we've learned. Now, while we're contrasting and comparing the discrete and continuous cases, I'll also mention that you can take expectations of continuous random variables, just like you can take them in a discrete case. But again, you have to calculate an integral using calculus. And so you won't have to do that in DMD, but know that the concept of expectation as a weighted average carries over to the continuous random variable case.